we've already introduced sort of the ideas what we're about to talk about. We just didn't name it, and that's potential energy. For example, we talked about a spring, and I said that if I squeeze a spring, I did work on the spring. Okay, well the work was stored in the spring, and so then the spring was able to push off and does the same work on something else. So it was storing energy in the spring. That stored energy is potential energy. In this case, the potential energy for a spring was, and we use the symbol U for potential energy, 1/2 kx squared. For gravitational potential energy, we said that we have an object, we lift it some distance here, we lift it some distance h. Well, it has some mass m, so if we go at constant speed, we have to have a force of mg. So the work we did on it was mgh. Well, if it's going at constant speed, it's not changing kinetic energy, therefore it changes potential energy. So this be the gravitational potential energy would be mgh. Okay, there's a variety of other kinds of potential energy, and so we can do, for example, several problems using potential energy. Now the thing is that if I lift at some distance mgh, then this object now has some potential energy, okay? And then if I let go, as it falls, it has less potential energy. Well, we know that energy is conserved because for every force is an equal and opposite force. And so if energy goes from someplace, it goes someplace else. Now, it could go into another object, or it could change what it is in the same form. So in this case, this would change from potential energy into kinetic energy. So the mgh would become 1/2 mv squared by the time it got down to the bottom. Well, the m's cancel, and so v is square root 2gh. Well, we've already run into that expression before when we were talking about just one-dimensional motion, and we just know that things accelerate downward g. Okay, so we've already kind of introduced that equation right there. But this is sort of our idea of potential energy. Now, what happened is the gravitational force, we had to do work against the gravitational force to raise it, so the gravitational force then converted the potential energy into kinetic energy. Now, this is a little bit different than another type of force, we talk about later, we call a non-conservative force. This is what we call a conservative force. So with a conservative force, then we would say that the initial energy in a system equals the final energy in the system. Well, the initial energy is going to be the sum of the initial kinetic plus potential, and that's going to have to equal the final kinetic plus potential. So this is our statement of conservation of energy. And so we can do several examples with that too. Now, and we'll do several examples using conservation of energy principles. But before I do that, I want to introduce one other idea here for us, and that would be a non-conservative force. So a non-conservative force. So with a non-conservative force, then that would be something like friction. So we have an object here, it's sliding, so that means it's got some initial kinetic and potential energy. Well, when it stops over here, the final kinetic energy is 0, the final potential energy, if this is level, the final potential energy is the same thing. And so that means that we have to have some kind of non-conservative work in here. Now, your book doesn't use quite this terminology here, but the book does indicate that you can have an external force. Now, an external force, so this would be this would be integral f dx right here, okay? And so the external force would either put energy into the system or take energy out of the system. In this case, friction took energy out of the system, and so that would be a non-conservative force. Same thing that actually happens if you look at just dropping something. You have something here and it's falling, it hits the ground, and the entire process, we have conservative forces. Now, that means that the kinetic plus potential remains a constant. When it hits the ground, however, it quits moving. And so now potential is 0, and the kinetic is 0. So what happened to all the energy? It certainly did not leave the universe. What happened is that in this case, when it stopped, we had other forces involved, forces that we're not looking at. And so what happens is, as it stopped, the top molecules kept moving down for a fraction of a second as the bottom molecules stopped. So the entire thing compressed. Then it expanded, it overshot, and so the molecules sit here oscillating. Well, if the molecules are oscillating more, what happens? Well, it's hot. Likewise with the case of the friction up here, what happens? The frictional force robs it of energy. Where does the energy go? Well, remember how friction works. It's an abrasion between the surfaces. So what it's doing is it's making these molecules along the surface vibrate, and so the whole thing gets hotter. This is kind of a classic example. Everybody has seen the police shows, right? You have the police show, and they find a gun somewhere, and so they say, I think this gun belongs to the shooter, and so they take it to the lab and they fire a bullet, and then they take the bullet and put it under a microscope and look for striations to match the markings of the bullet to the markings of a bullet found at a crime scene. Okay, and I watch these shows, and what happens is they'll fire the bullet here, and then they'll pick it up and put it under the microscope. It doesn't work that way. Because the bullet carries an enormous amount of kinetic energy. When it stops, the energy goes somewhere, and it dissipates into heat. That means the bullet is really so hot, it would be burning you if you tried to pick it up if it stopped suddenly like that. And so that would be another example. Now, we say non-conservative, it does not mean that the energy is not conserved. What it means is energy is going someplace we're not looking. At this point in the semester, we're not measuring temperature, so we're not seeing the energy go into heat. So we define basically two kinds of energy: mechanical energy and non-mechanical energy. Now, mechanical energy is going to be things such as kinetic energy, spring potential, gravitational potential, etc. Okay, basically, in order to be mechanical energy, you have to be able to describe the energy by measuring position, velocity, time, or mass. The sort of things we've been talking about so far this semester. If those quantities describe it, it is mechanical energy. And so, and I guess you can even leave velocity off, because velocity is just position over time. And so if those are the only things you need to measure, for example, kinetic energy, 1/2 mv squared. Okay, spring potential energy, you need to know how far you squeeze the spring. Gravitational potential energy, you need to know the mass and then how high it is. And so these are all examples of mechanical energy. Non-mechanical energy would be something like heat or chemical energy or nuclear energy or electrical energy, or a variety of other sorts of things. You know, the list just goes on and on and on. Okay, so any force that all it does, if all the force does is go from mechanical energy to another mechanical energy, so the force goes, between mechanical energies, that's a conservative force. And so that means you can say the initial kinetic plus initial potential equals the final kinetic plus final potential. Okay. Examples of a conservative force would be any force that is position dependent. That'd be like the spring force. So position dependent. Any force that is constant, so that'd be like the gravitational force that we've talked about so far, or any force that we call a central force. So a central force means it's directed only to or from a point. So that, again, this would be a positional force. Okay, it'd be just a positional force in 3 dimensions. And so in that case, these are all examples of conservative forces. And so that means this conservation of energy relationship there holds. On the other hand, if your force goes between a mechanical energy and a non-mechanical, so either way, either going from one to the other, that means we call that a non-conservative force. And in that case, you would have to say initial kinetic plus initial potential plus the work done by that force equals the final kinetic plus final potential. Now, energy is still conserved, and this is still a form of conservation of energy equation, but this extra term in there takes into account the energy is either coming from someplace that we were not measuring before, you're putting energy into the system from someplace else, or you're taking energy out of the system and putting it someplace else that we're not looking at right now. And so this would be an example of an open system in which energy going into the system or out of the system, or a case in which you're actually literally moving energy from one form to another form that we're not looking at, such as thermal, nuclear, or chemical. And so this is the basic sort of idea. So these basic equations right here are going to be the ones we're going to be using for almost everything in this chapter.